Now, this is a demonstration that looks at how the system copes with multiple degrees of freedom. So following on the introduction, using a single degree of freedom, here I will show you how to set it up for controlling, in this case, a vibration table that can produce heave or vertical vibration, as well as pitch and roll motion. So again, the first thing we do is we enable or configure and enable each of the degrees of freedom. The heave degree of freedom has already been configured. I can click on that and show you that it's the same as the previous demonstration. So we've set up the label, the feedback sensor, and so forth. So we enable it, and now we'll do the same for pitch. Again, we can label it what we want. In this case, the feedback sensor we're using is essentially an electronic gyroscope. It's an angular rate sensor, sometimes known as IMUs, inertial measurement units. But essentially we're getting an analog signal proportional to angular rate, measured here in degrees per second. We can also have actual angular displacement sensors in degrees, or a variety. We can configure this to suit any vibration test system. We here put the feedback sensor sensitivity. In this case, let's say it's a 300 millivolts per degrees per second. We remove the feedback offset, and we set our sensor channel to a different range. So in this case, we'll leave it to 10, plus or minus 10. We won't filter the signal. And here I enable the roll sensor in the same way. So usually these angular sensors, they come in angular velocity sensors, they come in multiple axes, usually 3 axes. Here we're using just 2 axes. So here we'll see that all the heave, pitch and roll have been enabled. So now we really need to set up the target PSD for each of the axes. The way this is done is again using Excel. So we've already done this. So we collected some heave, pitch and roll data from a small truck around Melbourne, and we've already configured the PSDs in there. So I can show you that. So if we right click on the PSD graph and we go edit PSD library, it will automatically open Excel, and you will see here the 3 axes. So this is the heave PSD, so there's a frequency and a PSD. There's a pitch and there's a roll. So channel number 1 is heave or vertical, number 2 is pitch, number 3 is roll. And here are the PSD values which we computed using well, any kind of software. You can compute using savers or any type of recording device. So how do we see each of the PSDs? We simply use this little radio button to swap screens. So essentially there are 3 screens which are superimposed. This is a pitch PSD, and this is a roll PSD. So these are real values measured from real experiments. We need to also set the RMS values. So for heave, I've set the RMS value at 4. So again, if I press edit on the RMS distribution or RMS dose graph, it will again open Excel, and you will see here the RMS. This is for heave, this is for pitch, this is for roll. Normally here in real life, you will have a distribution, so you will have different percentages along these columns. In this case, because we want to simply produce stationary or constant RMS vibrations, we simply allocate 100% to one level. So for heave, it will be all the RMS will be 4 meters per second squared, or around 4 Gs or 0.4 Gs. For the pitch, we've set it to 1.5 degrees per second RMS, and for the roll, we've set it at 2.2 degrees per second RMS. And of course, we can edit that here. It's Excel, so it's not difficult to do. We close this, and you will see this reflected here. So pitch was 1.5, if you look here, and roll, it should be 2.2. And that really is all we have to do. We set the test duration to a given value. We leave it at 1 hour here, and we start. In this case, it tells us we have an expected shaker displacement of 139. That should be okay. We can edit that, but we leave it to go for now. And the same for each of the axes. So you get these warnings or these reports for each of the axes, of course, and that's important. Yes, we proceed. Again, the system will now synthesize or create 3 random signals of 1 hour long each. And we've already measured the transfer function of the system, so we say use existing data. And that, of course, takes a little while. Okay, so now it's completed in creating the 3 signals, and we'll start the controller. So if we have a look at the Heave in the first instance, the system is now working. As before, we are seeing the actual running average of a PSD along with the target PSD, which is a red line, and the 3 dB tolerance. If we now, the advantage is we can switch between each of the axes. So here we'll see the pitch PSD, and of course the units are degrees per second. So as a spectral density is degrees per seconds per hertz, and we're seeing the roll PSD. Of course, this is only a few minutes, or in this case, a few seconds in a 1 hour test. So it will take a while for everything to settle down to the value. And one way to actually see how the system works is to have a look at the actual signals. So we have in the background information. So the first channel is Heave, and you can see here how you get an idea how the system works. It's essentially a follower. We have a shaker simulator hooked up here. We don't have a real shaker, so this is particularly good. But if you have a very good quality shaker with a good coherence and such as a good electrodynamic shaker, you will get this kind of results where the reproduced vibrations are very, very close to the target vibration. And this is for the pitch, and this is for the roll, and here the units are in degrees per second and meters per second squared. Our work has shown that the 3 quantities, Heave, pitch and roll, are in the time domain essentially uncorrelated. But in amplitude domain they are correlated. But this only comes into play when we use variable RMS or non-stationary simulation. For stationary simulations, which are essentially an artificial case, then the RMS levels are simply selected based on measurement or other arguments, and the system simply works as it does. So we'll stop this demonstration here. Hopefully that you found that useful, and please consult the company's website, realvibrations.com, for more information. Thank you.